The divergence theorem. The divergence theorem states, let E be a simple solid region and let S be the boundary surface of E, given with positive outward orientation. Let F be a vector field whose component functions have continuous partial derivatives on an open region that contains E. If all these things are true, then the double integral of f dot ds over the surface S is equal to the triple integral over the region E of the divergence of f dv. Let's recall that if you have a vector field f, which is equal to some pqr, the divergence of f is the partial derivative of p with respect to x plus the partial derivative of q with respect to y plus the partial derivative of r with respect to z. And let's also recall that when you take the integral of f dot ds, you are computing the flux. So this is another way of computing the flux of a vector field over a surface. So in the first example, find the flux of the vector field f over the unit sphere. Okay. So we know that the flux is equal to the double integral over the surface of f dot ds. That's also equal to the triple integral over the region of the divergence of f times dv. So let's compute the divergence. Let's recall that f here is equal to z, y, and x. And so this is p, q, and r. And the divergence is the partial derivative of p with respect to x plus partial q, partial y, plus partial r, partial z. So derivative of p with respect to x is 0. Derivative of q with respect to y is 1. And derivative of r with respect to z is 0. So the divergence here is simply 1. And so this is going to be the triple integral over the region R of 1 dv. Now let's recall that when you do a triple integral of the function 1 dv, you are simply finding the volume of your region, and your region is the unit sphere. So we know the unit sphere has a volume of 4/3 pi times the radius cubed, but the radius is 1, and so 1 cubed is 1. And so this is simply 4/3 pi. In our next example, let's evaluate the double integral of f dot ds over the surface S, where f is given to be this vector field, and S is the surface of the region E bounded by the parabolic cylinder z equals 1 minus x squared, and the planes z equals 0, y equals 0, and y plus z is equal to 2. Okay, so z equals 0 is the bottom, x equals 0 is this side over here, and that was y equals 0 is this side over here, and y plus z is equal to 2 is this plane right here, and then this is the parabolic surface that you see there. Okay? This integral would be really hard to compute because you have 4 different surfaces that you would have to find the integral of, and your function is really complicated. So let's see if we can do it by applying the divergence theorem. So we know that the double integral over S of f dot ds is equal to the triple integral over our region of the divergence of f times dv. So let's find the divergence of f. So again, we are looking at these functions. So we're going to take the derivative of this function with respect to x, that's going to be y, plus the derivative of this function with respect to y, which is going to be 2y, right? Because this doesn't have any y's in it, so that derivative is 0. And then the derivative of this function with respect to z is also going to be, or is going to be 0. And so our divergence here is simply 3y. And so this becomes the triple integral over the region R of 3y dv. Okay, now we're going to integrate this with respect to x, y, and z. We just need to determine what's the best order for doing that. So let's see, x varies between 1 and -1 here. Y is going to go between 0 over here and the curve y equals 2 minus z over here. And then z goes between 0 on the bottom and the paraboloid on top. So I'm going to integrate with respect to x last, and that will be from -1 to +1. And then I'm going to do z next because the boundary here, the paraboloid, is z equals 1 minus x squared. So I'm going to go from z equals 0 to 1 minus x squared next. And then we'll actually do y first. Y is going to vary from 0 to here, right? And that is y equals 2 minus z. Then we have the function 3y, and it's going to be dy dz dx. So I'm choosing an order of integration that flows with what I was given. Okay, so now let's go ahead and perform the integration. So let's focus on this integral here. Integral of 3y from 0 to 2 minus z dy. This is 3y squared divided by 2 from 0 to 2 minus z. This is 3/2 times 2 minus z squared, which is 3/2 times 4 minus 4z plus z squared, or 6 minus 6z plus 3/2 z squared. So now this next integral here will be the integral from 0 to 1 minus x squared of 6 minus 6z plus 3/2 z squared dz. This, of course, is 6z minus 3z squared plus 1/2 z cubed from 0 to 1 minus x squared. This will give us 6 times 1 minus x squared minus 3 times 1 minus x squared squared plus 1/2 times 1 minus x squared cubed. So now we have to clean that up. All right, so that's the first step there. And now let's go ahead and distribute and combine like terms. All right, so there it is. And so now we are going to integrate this function. With respect to x. Okay, you can probably finish this, but I'll go ahead and put the details here. All right, there it is, and you get an answer of 184 over 35. And that concludes this video lesson.